Good morning to those of you who are in Asia. Good early morning to those who are in Europe, and good evening to those of who are in the US. As you know, under the tireless efforts of Vito, we have assembled a stellar lineup of speakers, and Professor Yuen is no exception to this lineup. So what I will do is I'll leave you with a homework. You have to find out who is Professor Yuen, what is he doing. So the only thing I'll tell you is that he is the Associate Dean for Hong Kong Baptist University. He's a Chair Professor of Computer Science, and his research interests include video surveillance, human face recognition, biometric security, and privacy. So without further ado, Professor Yuen, we're an honor to have you here today. Looking forward to your talk.
Thank you very much. May I share my screen?
Yeah, please go ahead.
Can you see my screen now?
Yes, it looks
okay. Okay, thank you very much. Thank you, Chair, for the kind introduction, and also thank you very much, Archery Biometric Council, for the invitation. My pleasure to share my research work today. So I pick up the topics of face presentation attack detection. In particular, I would like to focus on one of our approaches. This is the remote photoplethysmography approach. Just simply called is rPPG-based approach. So this is the outline of my talk. First of all, I give a very brief introduction on the background and motivation why we work on this project. And then I give a very brief introduction on the basic principle for using rPPG for face presentation attack detection. And then I will share my journey on this project. And finally, I would like to give a conclusion. So biometrics have not been new for all of you here, and it has been extensively deployed in many practical applications. So right now, you can just spend $100 to $200 and then you can buy a fingerprint access control lock, and also has been successfully applied for border control for fingerprint, and also for iris recognition. Has been successfully deployed at a different airport, including the Dubai airport. In particular, during the pandemic period, users don't need to touch anything, but just go through the border, and then they perform the face recognition at a distance. Even more challenging task has been applied to a coal miner attendance, because normally the face is very dirty for the miner, and then the only thing that we can recognize is the iris. So on the face recognition side, the same. The face biometric also successfully applied in different applications too, including recently we also in Hong Kong we also offer the contactless e-channel. So again, because of pandemic, people don't want to touch anything, and then you just need to show the QR code, and then you walk through the channel with face recognitions. In China, also launched the first facial recognition ATM machine in China. And in fact, if we date back to 2017, the e-payment using face recognition technology was selected as one of the MIT technical review technologies. And along this line, many e-payment systems using face recognition has been deployed in the past few years. And then last year, also applied in fintech industry too. So while the biometric offer excellent convenience to the user, then it may have the security issue. So I find this video and news in the China internet news group, and then you may notice that even primary school students know how to fool a face recognition system, and they present the printed photo of his parent and then to the system, and then try to open the credit cabinet automatically. So if this is the case, then we need to ask one question: is face recognition technology secure? So in fact, the security issue is not new in biometrics. If you date back to 20 years ago, a research group in IBM already pointed out that there are 8 possible attacks on biometric system. So this plot diagram shows a very generic face recognition system, starting from you input the face, you go through the sensor, feature extraction, matching, the ones from the database, you get the result. So the 8 possible attacks, including, people can present a fake biometric to the system, replay old data, you can override the feature extractor, synthesize feature vectors after feature extractions, you can override the matcher, you can modify the template stored in the database. So the template here, we refer to the feature vector stored in the database. And then, of course, you can intercept the channel, and finally, you can override the decision as well. So this is a very generic system. So in biometrics, I would say 1 and 6 are very specific for biometric system, which including the fake biometric and also number 6, the template protections. So in this seminar, I mainly focus on the fake biometrics, in particular, present a physical fake biometrics or images, face image to the system. So for the face presentation attack detection, here, basically, I would say there are 3 popular attacks, namely the print attack, replace attack, and also the mask attack. So for the print and replace attack, basically, it's very easy because I can easily find other people's face, images, and also video from their social media, from the internet, and so on and so forth. And therefore, basically, it's a very low cost. I just download, print out the photo, and then I can fool the system. So the 3D mask attack is higher cost because you need to generate the 3D model and fabricate the 3D mask. And in terms of the cost for attack, it's relatively high. So, but still, it's still affordable. For example, right now, it's about $200 to $300. You can fabricate a 3D mask like that. And again, once they use the 3D mask, it may be hard to attack, hard to detect. So in order to solve this problem, if there's an image and video attack, then the straightforward approach is using, say, a 2-class classifier. So we just consider the detection as a 2-class classification problem. So we input the face, we try to extract features, and then we have the feature vector, and recently texture and also image distortion analysis were proposed. And after we extract the features, then it's just a 2-class classification problem to separate the real face and fake face, and then we get the answer. So along this line, many methods has been proposed in the past decade, including the appearance-based I just mentioned, the texture using LBP, the image distortion analysis, and also people also using motion-based. So if there's a fake image or fake video, basically you can ask the user to blink the eyes, to say something, so that we can detect the motion. However, this one may take more time, and user may not like it. Recently, deep learning also employed it for the feature extractions because we can automatically extract the optimal features for classification. So one of the very promising result is based on the central difference network published recently in PAMI. And while the deep learning is good, in particular for intra dataset setting, however, if you apply for cross setting, that may not be very good. So that's why another approach is using domain adaptation or generalization. We try to generalize the detection method so that it's also perform well on the unseen attack. And for 3D face recognition, of course, the straightforward approach is perform 3D mask attack for using 3D face recognition. So day back to 2017, Apple already launched the Face ID for the iPhone 10, and then they use the 3D face recognition. They claim your face is your secure password. So for in the iPhone 10, they use the structural light 3D technology to capture the 3D face information on face. So there are lots of sensors on the iPhone, and then including the projector and also one camera. The projector basically project a regular pattern on your face, and then because we have depth information on the face, and then after projection, the pattern will be distorted. Then we make use of the camera to capture the distorted pattern so that we can estimate the depth information of face. So along this line, Apple claimed that, okay, this is secure. So again, we want to answer this question, whether it's secure or not in this topic. For the 3D mask attack, as I mentioned, with the advanced technology on the 3D reconstruction and also 3D printing technology, and then once you have the 3D face model, then you can easily construct it, and then you can use it for 3D space spoofing. So this is one of the very popular masks can be fabricated from a company called That's My Face. This is the mask and also the researcher from the research group in the EDF, Switzerland, and she is actually my former PhD student, and this is her mask. And then for this mask costs about $200 US, and then in 1 week the company will deliver the mask to your office. And the first piece of work on 3D masks actually date back to 2013 by the EDF group in Switzerland, and they fabricate 17 masks and then try to plot out the score distributions. So from this score distribution on the imposter score, on the general score, and also the mask scores, you can easily see that the mask actually can fool the system. And the EDF group also evaluate different LBP method, different variations, traditional one, multi-scale, and so on and so forth. They found that it's a very effective to distinguish the real face and fake face. So there's another company in Japan. They also fabricate a super realistic mask. So here I give you 2 images. So can you tell which one is the real face, which one actually is the 3D mask, the fake face? So it's look very, very similar, super high quality. So this is the result. So the one on the left actually is the real face captured by camera. The one on the right actually is the mask face. So even people cannot differentiate because the texture, the eyes is super realistic. So in 2018, there's another data set created also from the EDF group from Switzerland. What I just mentioned, the 2 type of mask, hard silicon. So here, this is the soft silicon mask data set, and which also can be downloaded from their website. And this make the attack even more difficult to detect. So one question that you may ask is, oh, is it really people use the mask to fool the system? So here's the news on 2019 in Fortune. It's showing that 3D mask has been employed to fool the 2 payment system in China, the Alipay and WeChat Pay. And Alipay and WeChat Pay are the very popular payment system, e-payment system in China. And then we can fool the system, not only on the payment system in China, but also at the airport in the Netherlands, okay? And also the railway station in China too. So basically, it's happened already. People use the 3D mask to fool the face recognition system. So from now on, I would like to share my journey, on the face presentation attack detection using the photoplethysmography. I started this research on 2016, and then at the time the first piece of work actually based on the global rPPG technique. And after that, we find that global is good. The rPPG is good. We demonstrate it's reliable, but very sensitive to the movement, sensitive to the illuminations. That's why on the same year, we published another piece of work. We're using the local rPPG. And local rPPG is good, but rPPG, later on, I will mention that it's very sensitive to noise, the motion, the illuminations, and so on and so forth. So in order to reduce the noise interference, we have another piece of work on how to remove the background noise or the environmental noise by making use of the background informations. So in 2021, and then we also introduced the concept of multi-channel. We integrate the previous work and then propose a complete system or complete algorithm method using multi-channel local rPPG method with the background informations. The performance is very good, but there's one very big problem here is for rPPG. Later on, I will discuss it, and it takes a relatively long time to capture the signal. and then to draw the conclusion. Normally, it takes about 8 to 12 seconds. So which is may not be acceptable for some application, for example, for mobile device, for the mobile payment using Alipay and WeChat Pay and so on and so forth. So that's why we have another piece of work, how we can speed up the process. We have the new idea using the temporal similarity to have fast estimations. And after this piece of work, we find that the quality of RP signal is very important for the face presentation detection. So that's why this year we have another piece of work on the robust and generalization RPC estimation. So in the following, I will quickly go through this 6 pieces of work, and then at a very high level. If you have any question, you can write me, or you can refer to our publications as listed here. Okay, what is PPG? PPG actually is not a new technology. So it has been used in a clinic or hospital. So if you have chance to go to clinic or hospital, sometimes they have a clip on your finger to measure your heart rate. Actually, inside the clip, there's a camera to monitor the blood flow volume. Okay, by measuring the blood flow volume, the color, then we can estimate the periodic signal, and then we can estimate the heart rate. So this is the basic principle for the PPG. But we cannot directly apply PPG for face presentation detection because it is contact approach. So that's why we need to extend it to the remote rPPG. So the only difference is here is the camera will capture the face information, the face image at a distance. Then that's why we call that remote PPG. So after we capture the image, and then the basic principle for determining the rPPG, the heart rate detection is exactly the same as the original PPG. So the challenge here is once we have captured the image at the distance, there are a lot of interference, a lot of variations. So that's why I introduce a lot of noise. So that's why for most of the work in our research, we need to handle those interference I call noise. The next question that you may ask is why rPPG works on the face presentation attack detection. So this is actually a very fundamental for the high school biology, the skin architecture. When the light interact with our skin, we have the light skin interactions, and some of the light will be reflected to our eyes, and some of the light actually will transmitted to different layers of skins. Later on, it will interact with the vessels, but the energy, the proportion of light interact with the vessel basically is very, very small. And then the reflections after interaction, the reflection, and then go for different layer, and then go back to our eyes is even the energy is very small as well. But although it's very small, very weak signal, but still detectable. So if we put one more layers on the skin, which is the mask, then the process between the light and skin interaction is exactly the same. So the amount of light which can interact with the blood vessel will be even smaller. So that's why the reflected light go back to the eyes basically is undetectable. It's very noisy, very random, and undetectable. So simply speaking, if we can detect the RP signal after reflection, then it will be a real face. If not, then it will be the master face. So this is a basic principle. So because of noise, then sometimes, even though it's a real face, because of noise, we cannot detect the rPPG. So this is the research problem that we need to address. So here I show you one example of how the rPPG signal look like. This is the genius face, and this is the master face. And then we have detected RP signal. It's quite irregular. If we take the spectrum, in frequency domain, and then we can easily find that, okay, there's a peak, and this is actually the heart rate, and this is the real phase. However, for the master phase, still we can detect a different RP signal, but after detection, the signal actually is quite random, and the amplitude is quite small. If you look at the spectrum for this signal, it will be very random, and the power is very low, and that's why we cannot the peak of the spectrum, and then we classify this as a master phase. So this is a basic principle. So along this line, this is our first piece of work, very simple. So we detect the phase, and then for the phase region, we extract the rPPG signal in red, green, and blue, and then we go through a very temporal filter because we know that the heart rate for a normal person, say between 40 and 200 or 180. We just try to go for a filter to remove some impossible noise. After that, we do the FFT to get the spectrum. After we get the spectrum, we just use 6 parameters for recognitions, including the energy of R, energy of green, energy of blue, the power of RGB, the 6 parameter, and then we make use of the SVM for the classification. So which was our first piece of work in 2016. So the performance looks good. We make use of 2 type of masks, 3D Mac, and also the WIL-F, the 2 masks we shown before for experiments. And for the intra dataset experiment, the performance are excellent. However, when we perform the cross dataset, the LPP method, they perform very well in the intra dataset experiment, but not very well on the cross dataset. That means we train on one mask and test on another mask. However, for our pulse method, although in terms of the intra dataset, the error rate, half total error rate or equal error rate, or FRR, FBR and FBR at different FNR, the performance may not be as good as the LPP for the intra dataset, but for cross dataset, it's very consistent, give a very low error. And then we ask one question: why the performance is like that? So we look at the 2 masks again. The WIL-F, a super realistic one, the 3D Mac from That's My Face. We find that the texture on the 3D Mac mask, basically, this is something like the appearance look like the artifact from the 3D printer. But if you look at this one, this really looks like the real appearance for our wrinkles of like this. So that's why if we on intra dataset, the system or the algorithm will learn the artifact, the 3D printer artifact. And then if we apply it to the super realistic smart like this, and then the error rate will be very high. So that's why for cross dataset, the appearance approach may not perform very well. Okay, so we just simple experiment, simple result, simple algorithm, and then the result is very encouraging. We show that, we demonstrate that the global RP signal actually is good, but it's sensitive to some variation. As I mentioned, the illumination, the head motion, and also the video quality. So that's why we want to further extend the method to solve this kind of variations. So the next question that we need to ask is how to increase the robustness. Okay, so along this line, we propose a local rPPG approach. So the idea is as follows: we input the input videos, and then we also detect the face regions. And this time we need to detect the facial landmarks as well, because once we detect the facial landmarks, then we can divide the face into different local regions, and then we'll work on each local regions instead of the global face regions. And then we can extract, same as before, the rPPG value of red, green, and blue, and so on and so forth. So once we get it, then we will develop a local rPPG correlation model. So we notice that if for different local regions, the rPPG signal should be the same. Some are weaker, some are stronger, but they should contain the same rPPG signal. So that's why we develop a correlation model to remove the noise. So at the same time, the strength of different local regions are different too. So for those regions with very strong rPPG signal, then those signals will be very reliable. For those with weak signal, then should not be very reliable. Then along this line, we can generate the confidence map on the face, and then which we will use that for to train a classifier. Okay, so when a test image or video coming in, we go through the same process, and then we go through the local rPPG model, and the picture vector will be passed to the classifier, and then we can do the classification. So this is our local rPPG approach. So far, the local rPPG looks good for video like this, normal lighting, a small movement, the signal are good, and then we can correctly detect, oh, this is the real face. For the fake face, the signal quite random, and then we can reject it. However, for some situation, for example, if there's a strong lighting, strong movement, then the signal become highly corrupted. Under this scenario, basically, our algorithm fail. So the next question is how we can further reduce the noise so that we can have a more robust technique. So along this line, we have another piece of work. Basically, we go through the same process for local rPPG here. So extract the local signal, local rPPG signal, and also the pattern. But at the same time, we make use of the background information here. Because if there's an environmental noise, the noise contained in the background and on the face should be more or less the same. So if we can extract the noise here, and then we can actually learn the spectrum template. And this template, just like a filter, to filter out those noisy signal, so that we can obtain a very robust and clear feature vector here. We call this corresponding features. And this one will be used for classification. And we find that with the corresponding features, we can further reduce the noise. We further work on along this line and introduce the multi-channel spectrum concept. So the reason behind is when we talking about the phase, because the heart rate for a user will change on time. So, but for the background, it should be more or less the same. So if we perform some kind of time frequency analysis, we divide in different channels, and then actually this will provide additional information in designing the spectrum template, so that we can further boost the performance and reduce the noise. And this is what I call the multi-channel rPPG with corresponding features. And we perform the experiment again. Here we use 4 data sets, 3D map. This is that's my face mask. And we also have 2 in-house data sets. We call the HKBU mask version 1+ and also version 2+ mask. And this 2 actually has a more camera, more variations, and more mask. And also use the soft silicon mask, also from EDF group. And that's my face. This is the real F, and this is the silicon mask. So the variation actually, the variation actually is shown as follow. We have different objects, different videos, different type, and also different lighting conditions, and also different cameras, different resolution, and also different compression technique used for the video. And this is the work mask version 2+. Basically, it contains more videos, more variations on the camera too. So here's the result for intra data set. Same as the global technique. For intra data set on the 3D map, because it's a pure that's my face mask. The appearance-based method basically can learn the appearance very much, but still our technique, although we cannot provide the lowest half total error rate, equal error rate, and so on and so forth, but still not very bad. However, for the this is the for intercept for the mask version 2+, and which contain both different masks and also different lighting variations. Then along this line, our proposal method gives very good results. More importantly is we did a very comprehensive experiment on the closed data set setting. So we perform a lot of experiment with different data set, train on one data set and test on the others. Okay, and we also measure the half total error rate, AUC, BPCER at different APCER. So if you look at the closed data set experiment, basically our proposed method outperform all existing techniques. Okay, so that's why we can claim that our proposed method give a very good generalization, but in terms of error, may not give the lowest error on the intra data set. Okay, so what's the limitation for this one? Actually, it's on time required to get the result. So this research work actually triggered when one mobile device vendor visit our lab and saying that they are interested in our algorithm because it's a very simple, very computationally effective algorithm, does not require any require very expensive processor, but their concern is on the time. The question was, how long does it take to draw the conclusion? So normally, I would say we need to take 8 to 12 seconds. And then the question is, 8 to 10 seconds is too long. How about 2 seconds, even 1 second? So we did the experiment. We found that, okay, if for 12-second spectrum, then actually the performance is very good. But only for 3 seconds, basically, our performance was not very good. So that's why. And then the next question is how we can do it. This is reasonable because if you talk about, say, 60 minutes per minute, the bit rate, and then for one bit, just 1 second. So 1 second, basically, we cannot find the periodic information. So that's why if you look at the spectrum, it's very clear. So for the first few seconds, basically, we cannot find the periodic information until 7 seconds or 8 seconds. For 10 seconds, normally it's very good. 12 seconds will be the best. So along this line, we propose a new idea to solve the time problem. So we call the temporal similarity. So the idea is, if we given two genus phase and master phase, and then if we extract the local output signal, we try to find the correlation between the different signal attributes, for example, amplitudes. So if we, our idea was that in 1 second or 2 seconds, periodic information almost impossible to detect. And that's why a correlation may be one possibility. So along this side, we design our new features. Basically, it's a temporal similarity. We just calculate the temporal similarity between two time signal. So we find that the correlation signal actually is very good. Here is the distance. That's why the smaller the better. So that means here we can find the signal very much for the real phase. For the master phase, actually the signal, the correlation are quite random. We cannot differentiate which one is the, we cannot find the pattern. So along this side, we just extract the mean, standard deviations, minimum, and so on and so forth to form a feature vector, and the performance actually is very good. Along this side, we also applied it to two more attributes called gradient and phase. Okay, so we also found that their correlation are very good. Along this line, we further boost the performance. We introduced what we call the local consistent rPPG extractor before the extractions. So the idea is like that. Here we introduce, number one, we changed from the traditional calculated rPPG for the R signal. We design a deep learning, very simple deep learning framework to detect the rPPG signals. And then using the spatial temporal convolutions, which is quite, I would say, popular at that time, using the spatial temporal 3D network, instant norm, and then we do for extracting the rPPG. So at the same time, we also introduce some kind of consistency loss here. So our idea is for local signal, if they belong to the same region, the signals should be very close to each other. Then we can actually force those signals to some consensus, push them together. However, if those are the background signal, so the background signals should not close to the phase region rPPG signal, then we should pull them apart, put them away. And then here we further impose this constraint, and the result actually is even better. So based on this idea, we do some experiment and then evaluate the result, and they are quite consistent. So along this line, we actually further enhance the signal quality, or remove the noise using the consistency constraint, and we can reduce the correlations between the background and rPPG signal and also the phasal rPPG signal. So which is very good. With this experiment again, we also use the 4 data set for experiments, same as before. The mask is same as before. This shows some of the images from each data set. We perform the intra data set evaluations and also cross data set evaluation. In particular, from my point of view, cross data set evaluation is more important for practical applications. Okay, so this is for the intra data set. Here, we only take 1 second of the video and then do the experiment and compare with different rPPG technique. And we find that our proposal method greatly reduced the half total error rate during the development, half total error during the training, and also the equal error rate and also the AUC on both 3D match and also the HKBU mass version 1 data set. So we give a very encouraging for just for 1 second. So we also do the experiment for 1 second, 2 seconds, 3 seconds, and 4 seconds on the 3 data set. So as expected, when the number of seconds increase, the performance increase for each method. So our method is also the same. However, if we just focus on 1 second, our performance gain actually a lot from state-of-the-art rPPG, 10% improvement for the more complicated set, we have close to 20% improvement. Okay, so of course, if you go to 8 seconds, 10 seconds, the performance should be more or less the same. Okay, I like this record very much. So here we want to plot all the existing rPPG-based methods on the performance on intra data set and cross data set. So for these three figures, horizontal is the intra data set and vertical is the performance on cross data set. So first, let's look at the AUC result. So because this is the AUC, this corner should give the best result. So if you look at the current state of art of the face presentation attack, CDCN, I would say one of the very good algorithm perform very good result on the intra data set. However, if you look at the performance for cross data set, it's not very satisfactory. However, for our proposal method, as discussed, although we cannot give the very, very low error or high AUC on intra data set, but if you try to balance between intra data set and cross data set, our generalization ability are very good. This is our two method in the about the AUC. So about the equal error rate, basically a similar pattern can be obtained. For equal error rate, the smaller is better. So that means the best algorithm should be here. So our proposal method are here. And also, for example, for CDCN, give a very good very good equal error rate error for intra data set setting, but relatively high error for the cross data set. For the half total error rate, basically similar pattern can be obtained. Okay, so after we perform on this one, then we are thinking, okay, the quality of the RP signal estimation is very important. Then the next question that we need to ask is how to improve the robustness and also the generalization for RPT estimations. So here we need to address two problems. One is on the robustness of the RPG estimations on different, the illuminations, the movement, and so on and so forth. And more importantly, how we can generalize it for unseen interference. So in order to solve this problem, a straightforward solution is using the GAN-based, right? It has been performed well for the intra-data set evaluations. However, for unseen scenario, the performance may not be very satisfactory. Another approach is using unsupervised domain adaptation. So we can find the domain invariant features for denoise the signal. And it has been successfully used in the lecture images task. However, when we apply this technique on the RP signal, the time series data signal, the denoising, the noise reduction here may not perform very well. So that's why here we would like to propose a new piece of work and to improve the noise reductions on the RP estimations. In particular, try to improve the estimation quality. So the input to this algorithm is a spatial temporal map, which we discussed before. And then for the source domain, we go through the feature extractor, extract the source, and then estimate RPG. And then we can train the feature extractor using the ground truth rPPG signal. Okay, we have a ground truth PPG, and then we can train the feature extractor. So for the target domain, we go through the trained features, and then we go through the noise reductions, and then hopefully we can obtain the denoised target features. So the first bridge here is the adaptive noise reduction bridge. So we try to push the denoised target features and also the source features together, and then training the domain classifier. So this is the first bridge we want to obtain. However, this is good, but solving some, I would say, medium to easy noise. For difficult noise, it's hard to solve. And here we produce another bridge we call the complex noise generation bridge. Okay, so in this bridge, basically, what we want to do is we want to bring the noise in the target domain to the source domain, because in the target domain, we don't have the ground truth. Only source domain data have the ground truth PPG. So by bringing the noise back to the source domain, and then we can further refine and train the domain classifier so that it give this trained color will give the handle the harder noise. So to achieve this, we design in very simple adversary logic generations. We try to train the generator G so as to guide the learning on the noise reductions. So this is something that we achieve on this bridge. In order to generate more hard pattern or hard cases, so here we also propose what we call the hard noise pattern mining. So we try to reduce so easy a good high quality signal, and then only for those very hard cases we pass it to this bridge so as to train up the domain classifier to handle a complicated signal or complicated noise or hard noise. So using this algorithm, we perform experiment again. This time we are not using the phase presentation attack database. Instead, we're using the rPPG database, the physiological signal database, namely the pure MMSGHR, UBFC, and also the code phase. So these are the images or videos with different, gesture, different person, different motion, different tasks, and so on and so forth. There are lots of variations, illuminations, motion, expressions, different cameras, different videos, compressions, skin tone, heartbeat, and so on and so forth. So here's the result. So we follow the rPPG estimations task divided into task independent evaluations on the MMSE HR dataset, and also participant independent evaluation on the UBFC rPPG dataset. So if you look at the existing method and also the current state of the art, our performance actually perform very good because we try to learn and simulate so hard noise pattern so that even though some very hard noise, we can also train the domain classifier to handle that. So that's why in terms of the mean average error and also RMS, our proposed method outperform existing method. Also on the other data set, it's performed very well. Okay, so this is on the cross data set. So here we want to try, okay, what happens if we train on one data set and test on another data set? For example, here we show the result, train on MMSG HR data set and train and then test on pure, and then test on MMSG HR data set. Also, with using the same metric, mean average error, mean Rubin square, and also the correlation, Pearson correlation coefficients. So from all these results, we demonstrate that our proposed method actually give a very, very good quality of the rPPG signal. Actually, this video show, I forgot which stage we have, have a video to show that our algorithm actually can be implemented real time. This is although they call it an industrial grade camera, the key is there's no compression on the video output. It costs about $150 US for this camera, and then this is just a normal computer without a GPU card. So this is the video. Actually, he's my former PhD student, the mask, and this is the real implementations. The green showing that this is the real face. And the student tried to move around, see whether it's sensitive to motion, facial expressions, and so on and so forth. So when he put on the mask, we can detect that this is the fake face, the red color, and also moving around, see whether it's sensitive. So this is one of the videos we captured some years ago. Okay, so so this is the 4 or the 6 algorithm that we have shown, discussed. This is the timeline we mentioned before. So other than the rPPG-based approach, I also did some work on the other approaches. For example, on 2019, we also using the deep learning for extracting the discriminant features for recognition for detections. The performance was very good, and also we work on the generalization issue. As I mentioned at the beginning of the talk, generalization is the key problem for face presentation detection, because the attacker will not tell you how they attack the system. So that's why we have some work on the domain generalizations. We also further work on domain generalization issue using meta-learning approach. Recently, because of the GDPR, because of many privacy issue, we also work on the federated learning. We want to do some kind of collaborative learning. This is one of the work we proposed last year, how we can integrate the face presentation attack detection under the federated learning framework. In particular, we also tried the test time training. Here, we perform the test time adaptation, so to solve the problem. Okay, as I mentioned that our group developed some data sets. It's free to use for academic research. So if you are interested, just go to this link. You download the form, and then we will send you the link, and you can download the data set for experiment. Okay, so this is the conclusion that I would like to draw. I would say PET is very important and solve the issue in biometric system. In particular, if you want to develop a practical system, I think the detection is mandatory. In the past 5 years, the progress, I would say, is excellent. I didn't mention, actually, in the past 5 to 10 years, many new data sets also available. So you can download the data set, you can try the experiment. There are lots of interesting research questions can be done, can be answered, you can work on. I would say FacePack has a very high academic and commercial values. Not only academic like it, very challenging problem. At the same time, a lot of commercial product like it very much. In particular, if the computational power requirement is not high, then they're interested in that very much. And here I show that rPPG is a very good approach for the generalization ability for FacePack. Although it may not be able to give the lowest error in terms of the interest dataset setting, but the generalization ability actually is very good. So in practical use, we need to integrate other techniques to build a practical system. So again, rPPG also is a very powerful tool for healthcare domain, not only on biometric, but also in healthcare domain too. So I would like to thank my collaborator, Prof. Zhao from the University of Ulu, Patel from Johns Hopkins, and also my former PhD students. They did the work, basically, and also the funding source, Hong Kong Research Grant Council. Last but not least, I would like to spend 1 minute to do some advertisement. So all of you know that Biometric Council has transactions called the Archery Transaction on Biometrics, Behavior, and Identity Science. I strongly encourage, if you have new findings, very good findings, please submit your research work, research finding to our transactions. Very good transactions, welcome for submissions. Number 2 is about HKBU. In Hong Kong, we have a new, the government has a new initiative, try to attract very good students from all over the world, come to Hong Kong for PhD. And then if you are interested to work in Hong Kong, under our department are very strong in A, B, C, D. A stands for artificial intelligence and machine learning. B stands for big data and data management. C stands for computer vision and pattern recognition. D stands for distributed system and networking. So if you are interested in this 4 areas, you are welcome to apply our PhD position, in particular, the Hong Kong PhD fellowships. So this is a very, very prestigious fellowship initiated by the government. And although it's very competitive, but if you look at the scholarship amount, it's very attractive. That's why it's very competitive. The scholarship actually can be up to, in terms of Hong Kong dollars, it's 40,000. In terms of US dollars, it's around 40,000 is 5,000 US dollars per month. So very attractive, and also provide a lot of money to support your conference, visit, exchange, and so on and so forth. So if you're interested, please look at this QR code or go to HKBU Hong Kong PayFest. Then you can find the more detailed information, or contact me directly. Thank you. That's all I would like to share today. Thank you very much.
Thank you, Professor Yuen. Virtual clappings from me and the rest of the participants. So thank you very much for the exciting presentation. What I would like to do is devote some minutes to ask you the questions that have been posed in the chat, ask some of my questions, And then we'll close with Vito telling us about the IJCB 23 conference. So another set of advertisement, if I may. But it's all for a good reason. So thank you all. So Professor Yuen, the first question is from Lloyd, and they are asking, is the feature extractor in the model a standard encoder decoder architecture or something else? I'm not sure if you understand the question, but
yes, okay. I tried to understand and answer this question. So I think we didn't mention the feature extractions because we're using the before deep learning, we're using the traditional way to based on the RGB calculations to measure the RGB the RPG signal. So basically, it's not a deep learning approach. At the last piece of work, we multi-channel, we developed our, I think the first almost the first the deep learning approach. That is basically based on the spatial temporal encoder. Okay, so this is a very simple and very computation efficient method. So it depends on what you want to do. If you want a very large model, very light computation, you can follow the traditional way, I think developed by Philips more than 10 years ago. If you more sophisticated data-driven approach to learn the feature extractions, then you can use the deep learning approach. And even for deep learning approach, is also very simple, very computationally efficient. So that's why rPPG is a good way to go. The most important issue is how long does it take to get the satisfactory result. That's why we have the a fast rPPG estimation method. Yeah, I hope I answered the question.
If Lloyd has a follow-up question, he's welcome to post. So the next question is from Teresa, and she's asking, can generative AI be used for the domain generalization problem?
I think so. This is a good idea. I think so. Because very often we need to generate more samples. And then if we can generate and model the variations that cannot be seen, we can solve the generalization problem. So when I present our last piece of work on the this year's CVPR work, this is the idea. We want to generate some hard noise, which not seen, not trained before, so that we can make use of the hard noise to train the domain classifier. So basically, it's a generation approach. Okay, so how to generate is the issue we need to discuss, but the direction we should go along that line. Yeah.
Thank you. So the next question is basically asking, what happens when you use rPPG on replay dataset, which contains similar rPPG information?
Sorry.
What are your insights for this problem?
This is from Zhong, right? Is
yes.
The question? Okay.
Yes.
Let me read that. Yeah.
Zhong Xiong.
Oh, okay. So my topic is, sorry, give me a second. I read the question.
You're welcome to read the question.
Oh, yes. Very good question. So rPPG signal actually happen and contained in the video. Okay, so if you just capture the video, and then you can also capture the rPPG signal. So we have one piece of work also evaluate how we can really do the generalizations. Okay, that means if I train only based on rPPG, can we generalize it to image attack, replay attack, and also mask attack? So rPPG, I would say, is very good for image and also for the 3D mask. 3D mask, I would say, mask attack is very good. But for video, we need to add something to integrate into method so as to solve the problem. So if you want to develop some kind of practical use, then that can be direction to go to integrate something, some other algorithm with the rPPG, because rPPG provides very good generalization ability. So at the same time, and one piece of our work was we make use of the background. So if this is a video, this is a replay video, all the rPPG signal or the I would say the periodic signal from the background, from the face should be the same. So you can make use of this information to cancel out the data, the noise. And this is the work, the idea we use for the CV, I think ECCV 18 work. We make use of background information to remove the noise, including those periodic noise, environmental noise, and so on and so forth. Yeah. So this is something that you may consider too along this line.
So thank you. You talked about the practicality of the system, and forgive my ignorance, but how big is the camera that you need to obtain the rPPG?
You mean the resolution or?
No, how big the size of the camera?
The camera. We just use a normal webcam. When we do an experiment,
The smartphone camera can do the same job?
just normal RGB camera.
Okay. So
yeah,
can it be used indoors and outdoors or just indoors?
Oh, right now we mainly focus on indoor.
Okay.
For the video.
What is your prediction about what will happen when you get an outdoor data set?
The illumination problem will become more serious. Yeah. And so far, we didn't test on outdoor, but normally indoor. But
Okay,
we
so
tried
the
different
next
cameras.
data set we're going to release is about outdoor images.
Yeah,
outdoor.
we need to maybe construct an outdoor data set.
So
I think it's a good idea because if we really put in real application, we have to handle the outdoor scenario as well. Yeah.
okay, so since I don't see any other questions, I'll dare to ask. Looking at your crystal ball, I guess it was deep learning using transformers, then it's deep learning using diffusion models. What's the next topic in deep learning?
Sorry, I missed it. Sorry.
The deep learning and transformers, correct? We
Right.
saw the rise of deep learning and transformers. We saw deep learning and diffusion models. What's
Well, I don't have
I understand I'm asking you to predict the future, right? So
I don't have the crystal ball, but from what I heard and what we have read the articles and also some preliminary results from my students, transformer actually a very good approach to solve the problem. Sometimes outperform ResNet, the CNN base, and I would say for me, I think we can, it depends on application. I think again, I don't have crystal ball, but transformer is one way to go, and the diffusion model, the generative model is another way we can further generalize the algorithm, because we can generate more data and more like what I mentioned, our CVPR work, how to generate harder cases, unseen cases to train the network is important. And then with the advanced architecture, I think it can be learned. So this is again only my very preliminary naive idea.
I thank you. What I heard from you is conjunction of transformers and diffusion models. Okay.
Right.
So I also have a question.
Yes.
I was wondering, so in all, let's say, models that address presentation attacks, generalization is one of the main issues, right? So you need to generalize from your data or the capturing devices you have to maybe other attacks, other capturing devices, and so on.
Right.
And if you learn like the models in a discriminative way, this usually limits it a bit to a type of attack, right? Or a type of so manipulation that you see. So I was wondering, how do you feel about rPPG signals being used in a sort of one class setting? So learning just from real images or real videos in your case, does that make sense in this problem domain?
Oh yes, this is a very good question, and this is also a question asked by one of the the mobile device vendor. The question is, can we use near infrared? Can we use other spectrum for detection? Because it's for detection. Then I think the idea is good to make use of say near infrared and also other spectrum for detection, but not just traditional RGB input. So I totally agree. And I didn't work on that because of two reasons. Number one is, for me, practicality is one of my concerns. So for the presentation attack detection should be, before recognition. Then if you have an algorithm which need to change all the existing setting, then people would not use it. From research point of view, I think it's totally fine. From the practical point of view, existing system, they may want to change the input camera and so on, so because once you change the camera, the recognition part may be introduced another problem. So that's why I prefer to make use of the conventional RGB camera, which used for face recognition. Of course, some system also use the near infrared camera. So that's the first reason. The second reason is we don't have the data set. That's why we didn't check it. One day I tried to convince my students to do it, but they are too busy. And then yeah, if we have this, I'm happy to try to work on that. Yeah, I think the input source is another issue which could make the problem or simplify a bit on the problem, in particular solving the generalization issue. I fully agree.
Okay, so maybe another question. So if someone would start working on similar problems like rPPG signals for presentation attack detection, what would you say is like the three main open issues that you see still in this area that needs to be resolved?
The three main issues, right? For presentation attack detection, generalization ability certainly is one thing. Number two, from our experience, the video quality, not the resolution, but the compression. We try, as I mentioned in the demonstration video, we try the ordinary web camera, like those cost maybe $100 used on a desktop, and normally the output actually is a compressed video. For rPPG on compressed video detection, sometimes it's not good. So that's why when we really do the real demo, number one, we want to have a high frame rate camera, and number two, they can output uncompressed video. So the video compression is another issue. And one group in the ULU, also have one article to address the compression issue. So right now we have many research work try to address some different, I would say, specific problem in rPPG. But again, it's an integration problem or generalization problem. How we can develop one generic method to handle all these variations is the biggest problem. For me, I think it is a good way to solve one unified rPPG algorithm to handle compressions, head motions, illuminations, outdoor, and so on and so forth. So this is a big issue. Not talking about the camera issue. Yeah. So this is my comments on that.
Okay, thank you for the insight.
Thank you, Professor Yuen. I don't see any questions in the chat. Vito, do you have any more questions, or you're ready to tell us more about ITCB23?
No, I don't have any questions. So I'd like to thank Professor Yuen again for the nice talk. It was really
thank you very much. If you have any questions, please write me. I will try to answer through emails.